Hello everyone, I'm Yichen Jiang from ARM Austin office. Today I'll talk about our paper Performance Bottlenecks and Potentials in RocksDB as Storage Component Evolves from Flash to 3D Crosspoint. This work was done during my PhD study at Louisiana State University with Dr. Feng Chen. This is the agenda of this talk. I will give the related background first. Then I will discuss the motivation of this work. Next, I will show the methodology of our experiments. Then I will show the performance bottlenecks and potentials we identified. Finally, I will conclude this talk. Data centers are designed to host information systems and related components such as servers, routers, storage, cooling units, and power supplies, etc. Data centers are becoming popular because of the booming of mobile devices, IoT devices, and 5G technologies, etc. From this figure, we can see that the number of data centers has increased almost linearly from the year of 2013 to the year of 2019. There were over 500 hyperscale facilities worldwide in the third quarter of 2019, and most of those facilities are distributed in the United States. Asia Pacific and European countries also account for a large portion of them. As for the storage component in data centers, traditionally, hard disk drives play a dominant role in providing the data services. However, according to a recent study from IDC, the distribution of bit shipment share by storage media type shows that flash-based SSDs are becoming increasingly popular in the recent decade. As the figure shows, the bit shipment share will reach about 40% by the year of 2025 by flash SSDs. So SSDs are eroding the HDD's long dominant position in data centers. Flash-based SSDs have several unique properties. Different from hard disk drives, SSDs remove the rotating mechanical parts and are totally based on semiconductors. So they can provide high throughput and low latency, and they are suitable for the parallel operations. However, they still have several limitations. Read-write speed disparity is obvious. The random write operations are notoriously slow on SSDs. No in-place overwrite is allowed. That means all the pages have to be erased before being programmed again. And all the writes have to be organized in a sequential order to keep the efficiency. So the software designers have to be aware of these unique features to make the software flash-aware. Key-value systems are a kind of applications that are suitable for flash memory. These systems use simple yet efficient key-value model which uses a unique identifier to find the corresponding value by searching the key-value mapping data structure. For example, the key can be a user ID and the value can be a username. Also, the key can be a URL and the value can be an image. As for the key-value stores, they always use a log-structured merge tree to manage the data. Famous examples such as RocksDB from Facebook and LevelDB from Google are widely deployed. So the flash-friendly LSM-tree is gaining popularity in data centers. As for the log-structured merge tree, it can exploit the fast sequential access speed of disks. It is particularly optimized for write operations. It works like this. A write will be written into memory first, then logged in the write-ahead log on storage for consistency. All the writes will be accumulated in the Memtable until it is full. Then, this Memtable will switch to immutable Memtable. This immutable Memtable will be flashed onto storage in level 0. There is an expensive process which is called compaction between level 0 and level 1 to remove the obsolete and deleted data. Similarly, there is a compaction process between level 1 and level 2. The difference between level 0 and other levels is that files in level 0 may have overlapping key ranges, while files in other levels all have unique key ranges. As for the read operations, it will check the metadata in the manifest file first, then fetch the corresponding value in the write location. This data structure is particularly designed for disks, and it works well for flash. However, the storage never stops evolving. The newly announced 3D crosspoint technology is believed to break the memory and storage barrier. The latency of 3D crosspoint is between memory and NAND flash. The latency can be about 100 times better than NAND SSD. In order to keep the back compatibility, vendors also proposed 3D crosspoint-based SSDs. These SSDs also use block interface, but it can provide symmetric read and write speed. The latency can be as low as 10 microseconds, and the throughput can be up to 2.5 gigabytes per second. Also, the reliability improves a lot. This is the motivation of our work. At the hardware level, the latest storage advancement, 3D crosspoint SSD, have been available in the market. The limitations on flash, such as read-write disparity, slow random write problems, have been highly elevated on 3D crosspoint. At the software level, RocksDB is particularly optimized for flash, and it is widely deployed in data centers. So here comes the question, is flash-optimized RocksDB readily applicable to 3D crosspoint SSD? This is a simple motivating example. We benchmark the performance of random read-write on 3 kinds of SSDs, including SATA SSD, PCIe SSD, and 3D crosspoint SSD. We found out that the raw device performance has increased about 16 times on 3D crosspoint SSD than SATA SSD. However, the corresponding performance on RocksDB only increases about 77%. It clearly shows that there exist performance bottlenecks in the system that hinder us from fully utilizing the performance benefits of the new hardware. This is the methodology of our experiments. We use a typical server which is equipped with 2 8-core Intel Xeon CPUs. The DRAM we use is 128 gigabytes. We use 3 kinds of SSDs, which include SATA SSD, PCIe SSD, and 3D crosspoint SSD. At the software level, we use Ubuntu 14.04 as the operating system, and we use kernel 4.4. We use ext4 as the file system, and RocksDB 5.17 as the database. We use dbbench, which is the default benchmarking tool in RocksDB to generate the workloads, and each experiment runs for 300 seconds. In the next session, I will show the performance bottlenecks and the potentials we identified in our experiments. This figure shows the workflow of RocksDB. The applications send the read-write requests to the system, and the monitor component will monitor the incoming traffic. All the writes are then accumulated in the write buffers. When the write buffer is full, the updates will be flushed onto storage. Through our analysis, we identified 3 bottlenecks in the current software design. In the workflow, we find the bottlenecks reside in all the 3 components listed in the figure. The first bottleneck we identified is called the throttling mechanism. We benchmarked the system with 2 workloads, with 90% writes and 5% writes respectively. From the figure, we can see that there is theoretical performance drop when the workload has 90% writes on all the 3 devices. In particular, the throughput variation on 3D crosspoint is clearly evident. The throughput can be as low as 3 kops, which makes the system almost unusable. When the workload has 5% writes, we can also observe the performance fluctuation on the 3D crosspoint SSD. We try to explain this phenomenon with the following figure. The monitor component in RocksDB try to maintain the incoming traffic almost equal to the background processing traffic. So we can have the relationship between lambda A and lambda S. With a simple arithmetic transformation, we can know lambda A will change according to lambda S. On 3D crosspoint SSD, based on our calculations, we can see that lambda A can become as low as 2.7 kops. which is very close to our observations. In order to elevate this problem, we proposed our first pilot solution to try to remove the near stop status. We upgrade the throttling method into a two-stage one. In the first stage, when the number of level 0 files reach a threshold, we will trigger select throttling to reduce the read rate to the maximum acceptable one. In the second stage, when the number of level 0 file continues to grow and reach another higher threshold, we will trigger an aggressive throttling to further reduce the read traffic to a lower level. We tested our method with a workload with periodical read burst and found out that it can remove the near stop status effectively. The second bottleneck we identified is in the Memtable management mechanism. For the same amount of space, if the file size is larger, we will expect fewer files. On the contrary, if the file size is smaller, we will see more files. Surprisingly, this setting will have opposite effect to the read and write operations. For the write operations, smaller and more files will have shorter latency, while larger and fewer files will have longer latency. For the read operations, it is totally opposite. Smaller and more files will cause longer latency, but larger and fewer files will cause shorter latency. We would like to explain this phenomenon with this simple example. With the same amount of data, let's say 9 items, we can either use a large sorted file to manage them. In this case, we only need one binary search on this large file to find the requested item. Or we can use 3 smaller sorted files to manage this data. In this case, we need 3 binary search on these 3 smaller sorted files to find the requested item in the worst case. As a consequence, the time complexity of read operations has increased from big O log k times n to big O k times log n. And for the write operations, the time complexity has decreased from big O log k times n to big O log n. That's why the level 0 file setting will have opposite effect to the read and write operations. In order to elevate this bottleneck, we proposed our second pilot solution, which is called dynamic Memtable setting, to make use of our findings. We will measure the read and write ratio of the workload during runtime to determine whether it is read-intensive or write-intensive. For the read-intensive workload, we will set larger yet fewer files. For the write-intensive workload, we will set smaller yet more files for the level 0. With this simple method, we can observe a 13% performance improvement compared with the original static setting. The third bottleneck we found is in the read ahead log. Every update to RocksDB is written into 2 places, namely an in-memory data structure called Memtable and the read ahead log on disk. In the event of a failure, read ahead logs can be used to completely recover the data in the Memtable, which is necessary to restore the database to the original state. In the default configuration, RocksDB guarantees consistency by flushing the read ahead log into page cache, the operating system memory, after every user write. Since 3D crosspoint is dramatically faster than flash devices, we expect the logging overhead will decrease. However, we find out that the logging overhead doesn't reduce as the above figure shows. Read ahead log has a significant impact on the write performance on 3D crosspoint SSD. This is because the read ahead log will be flushed to the page cache first and then synchronized to the disk later. The read ahead log in the page cache can guarantee the consistency when the application crashes. Although read ahead log causes overhead to the system, we cannot simply disable it because of the consistency requirements. In order to elevate the logging bottleneck, we proposed our third pilot solution, NVM logging. We use a faster and persistent NVM device instead of SSD device to store the updates. The NVM used in our experiments is simulated using DRAM. As the figure shows, since the frequent read-ahead log updates are redirected to a faster device, we observed an obvious latency reduction with this simple method. To conclude this talk, first, we have conducted comprehensive experiments to understand the performance impact of the dramatically faster 3D cross-point devices on RocksDB. Second, we have observed the performance bottlenecks and potentials of RocksDB with the new storage technology. Third, we have also provided explanations for the observed performance bottlenecks. Finally, we also developed 3 case studies to showcase the performance optimization opportunities based on our findings. Finally, I would like to thank all the reviewers for their constructive feedback and insightful comments. I also want to thank all the sponsors for their generous fundings. If you have questions about this paper, you are welcome to contact me at this email address. Thank you.